So let's start what we studied before. So the Gallerian transformation, preserving t square minus x square is the inner product. Then according to Gallerian transformation, x change into such like that, and t change into such like that. Then their inner products, they're invariant, kind of Gallerian transformation. Then writing such kind of transformation in terms of the matrix, and we compare with it with Lorentz transformation, then you found that V equal beta x. So beta related to rapidity related to velocity in Lorentz transformation in leading order. Then we divided some fields in how to they behavior in Lorentz transformation. So scalar field invariant field under Lorentz transformation, such as the temperature, and pole vector is a kind of the coordinate or momentum or velocity. So it depends on Lorentz transformation. Vector field also depends on Lorentz transformation, but it's some kind of the function on coordinate. And their mixture also depends on number of index. So if there are no index without Einstein summation, then their variation, their mixture of the fields behavior like a scalar field. And we can also consider many indexes in one function, then we called it tensor field. So in this T mu nu sigma rho is a rank 4 tensor, and also we can call same index twice in tensor calculation. It's called contraction. So if all indexes contracted to each other, then that is behavior like scalar field. And I also show that Lorentz invariant for inner products. Okay. And the Allen-Cartesian is a four-dimensional version of the Laplacian. And I also show that Lorentz invariant quantity, Lorentz covariant quantities. So today I'm talking about the discrete transformations. So discrete formations are the kind of the transformation that included Lorentz transformation, but it preserving Minkowski metric. So normally we called Lorentz transformation is preserving Minkowski metric. then so just note about it. lambda e lambda equal g, and also Laurent transformation preserving inner product. Sorry. Read again. Equal to V0, 0, W1, V2, V2 minus this one. But we can consider two transformation or the transformation, satisfying preserving Minkowski metric and inner product. Two other transformations. Satisfying these two conditions. One is a parity, denoted by T, X, Y, G. This change into T minus X minus Y minus G. And second one is time reversal. T X Y G change into minus T X Y G. So I think this is very simple things. So you can easily show that this change preserving Minkowski metric and inner product. So in terms of the form of the matrix, is T parity transformation T. But this is important thing about A, this one. Is do not combination of rotation and boosters. And there are three vectors. So this is a discrete transformation, and also then I introduce there are three kind of the vectors. We can categorize them. One is a time-like. So their inner product, time-like vectors, always larger than zero. For example, equal to 1, 0, 0, 0. Then second one, space-like. And their inner product always smaller than 0. So their example 0, 1, 1, 1. And the last one, line-like. To 0. For example, this is a kind of the particle satisfying p square or m square. So massless, like a photon. So this can be we write down in terms of the right cone. So this is origin. Right cone and the time-like vector, such kind of the vector. You just simply write down T mu, time-like T, and space-like a kind of the vector like this. V, space-like, and line-like, just the same line on the right cone. This is line-like. So normally for just physical matter, it can be time-like vector or line-like vector can describe. So we need to solving a physical problem. Then in this process, the Lorentz invariance is very important property to solving physical problem and reproduce their result. 3, 2, 1, 4. Solving problem. with Lorentz invariance. So we need to change the frame in our frame to another frame. So this implies that according to Lorentz transformation, G. So a Minkowski metric in our space-time changed by Lorentz transformation, then it produces just Minkowski metric. So same way, the scalar field or scalar value does not change in terms of the coordinate transformation according to Lorentz transformation. So such kind of the transformation implies that some change in frame couldn't change, but the problem, the important thing in this case, vectors will be changed because all coordinate system depends on Lorentz transformation. So vectors will be changed because they having a one or more indexes. But scalar quantity such as p square, size of the momentum, or some contracted value, something like that, will not be changed. So they are the same to all frames. Interestingly, this is still satisfying even if we didn't know about information about the frame in unknown frame. So Lorentz invariance very important things when we study about the physical quantities and making a problem simple. So now let's move on to the more close to the second quantization. So in previous chapter, we consider some electromagnetic wave is a many-photon system. So when we interpreted some kind of the quantum multi-particle system, then we consider there are many quantum waves are in some space-time, like oscillators. There are so many oscillators in our system, and their oscillators will be given by quantized oscillator. So classical So we will consider classical plane waves as our oscillators. Then we generalize it to quantum system. Oscillators. So the relation between the classical plane wave as an oscillator, you just thinking about the black body radiation what we studied before. We consider simple harmonic oscillator. Then this describes the photon field. But the photon field itself, the electromagnetic wave, so we electromagnetic wave as a plane wave. Then the plane wave can be interpreted by simple harmonic oscillator. So oscillator system describes the plane wave system. Then we generalize to quantize the system. Then we can find many particle quantum field system. First, let's visit about the simple harmonic oscillator in classical view and quantum view. So it is one simple harmonic oscillator. The simple harmonic oscillator in classical view, they having a restoring force. And it is conservative force. So let's first visit about the classical view about the simple harmonic oscillator. So their equation of motion mass of the particle, acceleration depends on the restoring force. So its solution simply xt as a function of time sine omega t and omega root k over m. And its general solution I think you already studied about such kind of solution in mechanics. Potential I omega t plus C2 E omega t. And such kind of the system, the Hamiltonian operator, H equal to 1 over 2 B square plus 1 over 2 M omega square X square. The quantum view this kind of the simple harmonic oscillator. Now we quantum view the important things the commutation relation. In small or low energy case, the commutation relation not to be zero. So we should consider about the commutation relation. For example, x comma p or I. So in quantum physics, you already study about the lowering and raising operator. M E M omega. This gives, I think it's just some review about the quantum physics, so I do not talking about the detailed things, how to be calculation about such kind of computation relation, how to avoid and Hamiltonian operator, but you can easily find if such kind of the A deco to classical uh, Hamiltonian, then you find out how to write down Hamiltonian in terms of the raising rolling operator. to A 되고 A and the number operator or state variable n equal to n and A 되고 behavior like this A n equal to root n minus. So from this, we need to find when we raising or lowering some state and how to their state depends on time. So we trying to obtain the time evolution about the operator A in the Heisenberg picture. So this is according to Heisenberg picture, the equation motion for operator satisfy I eta satisfying commutation relation for A and H. So the equation to satisfying A operator satisfy A omega A 되고 A plus 1 over 2 and omega is just a number can move out and then A 되고 A plus 1 over B minus A 되고 A plus 1 over 2 A. Then this can be omega A 되고 A minus A 되고 A omega A 되고 A. So this is just omega A. So for time evolution for this operator, then we found that AT is a solution. So A operator depends on time such a way, but exponential I omega t kind of the plane wave solution. So operator A something behavior like plane wave solution, plane wave like behavior in for the time coordinate. Then let's relate it to special relativity. Connection to special relativity. So such kind of the plane wave solution, we can find some vector field, for example, scalar field, that is equation, very simple equation motion for scalar field. Equation motion having oscillating solution such a plane wave with Lorentz invariant equation for scalar field with Darlang position. According to as a definition of the Darlang position, Darlang position pi equal to round t square Laplacian scalar field depends on time and spatial coordinate equal to 0. So the solution about the pi equal to pi px equal to some operator giving a momentum p and time dependence and I momentum p. This is a simple solution about the plane wave with coordinate x1, x2, x3. Then if we input this scalar field solution to the equation motion, then you found that Darlang position pi equal to partial derivative t square And Laplacian shows that IP square, so that plus P. And AP time function do not depend on the spatial coordinate. So you just leave it here and exponential kx. And this is equal to. Once again, the P also operator minus I round x. So scalar field depends on some amplitude or some operator AP, P, and their locations. So it kind of some plane wave solution for spatial coordinate, and it is also time dependence on operators. It is just some example of the solution. Then we go to more general solution to find as what we already study in simple harmonic oscillator in classical point of view. We can consider general solution for kind of the simple harmonic oscillator. So we generalize to the quantum generalized solution. Let's go to general solution. Using Fourier decomposition. So let's Fourier decomposition to this such kind of the solution, general solution. Then the pi xt equal to e a p p x. This is just one solution, and we already used some generalized solution for this. It is r minus I p x. So using Fourier transform decomposition, we generalize all kind of the momentum to the all kind of the momentum. Okay, so we finish here, and then we will study about such kind of the general solution in terms of the tensor notation. That is a more simpler way, and also can how do we define this scalar field to describe the what kind of the particle having an energy. Okay, see you next time.